Good morning. I'm Guzhi from Shanghai Jiao Tong University. So I'd like to thank organizer first to bring us to this nice city, and also have me here to introduce our work about quantum magnetic gradiometer with entangled twin light beam. So if time is enough, I'd also want to introduce a bit about our work with quantum magnetometry with spin squeezing. So I will introduce the background first. So we are OPM community. So we both know there are a lot of applications for magnetometry. Like in fundamental physics, people study like coupling between nuclear spin, atomic spin with the exotic field. Like being biomag, I'm pretty sure we will have a lot of discussion about how to measure biomag with OPM. And for geology, we can measure the Earth's field, and the applications for astronomy and material science. For all of these applications, we always want to have a lower sensitivity for magnetometry, but we will meet some fundamental limit for the sensitivity. This is called standard quantum limit. So optical magnetometry are also somebody called atomic magnetometry. So from these two names, we can know the particle to measure the field is related with atom light interaction. So to measure the field, we usually initially use a circularly polarized pump beam. It's on resonance and transfer the angular momentum from light to the atom and polarize these atoms. Then after the polarization with the existence of external magnetic field, so the atom will undergo lumbar precision. So the precision frequency is proportional to the magnetic field, so amplitude of the field. So that's how we know the field. But we cannot directly see an atom is rotating like this, right? So we need to use external light field. It's a probe beam. It's a linear polarized far off resonant light to interact with atom using Faraday interaction. And this will map the spin state of the atom to the polarization of the light. So then we measure the light, we know the field. So from this process, the thing directly measure the field is the atom. So with the coherent spin state, this is limited by spin projection noise. It's 1 over square root NA. NA is the atom number. And the thing we measure is the light. So with the coherent light, this will be limited by photon noise. It's 1 over NP. NP is photon number. So with these two, they are jointly decide the quantum limit of the sensitivity. So from these two equations, we can directly see a simple way to improve the sensitivity, just increasing these particle numbers. There's another way, like we can use quantum technology like squeezing or entanglement to break this limit. So why we not just simply just improving this particle? Why sometimes we want to squeezing? So for example, if initially we have a very low particle number, for example, it's 100, we can improve the sensitivity from like standard quantum limit to Heisenberg limit by like squeezing. And we will get a metrological gain. It's, for example, if the number is 100, it will be 10, improve 10 times. But in the classical way, we can just like increase the particle number. It's not so difficult, like increase the number to 10 to the fourth. Then we can get the same sensitivity. But if we already have very large particle numbers here, it's for the like quantum technology, it's also improved 10 times. But for a classical way, it need to also 2 orders of magnitude improvement, but it will need to increase 10 to the 10th number of particle. So this is much more difficult than this one. So in this situation, the quantum technologies has more advantage. And there are 2 very good examples for the quantum technology. One is the microscope. So if we use microscope to measure some cell, so this cell cannot stand too much optical power. This light will burn these cells. So at this situation, it's keep like increasing the photon number is no longer an option. So this will burn the thing you want to measure. So in this situation, if we want to improve sensitivity, the only way is the like quantum technology. So another example is LIGO. So in LIGO, they need to measure very weak signal. So they already use a very high optical power. And in this situation, they will face a problem like the fluctuation of the amplitude of the light while pushing the mirror, and this will feed back to the phase measurement. So this is called back action. So now you can also increase the optical power, but with the increase of power, the sensitivity cannot be improved. So here is also a good example to apply the quantum technology. So these two examples are both metrology based on optical field. It's the same as the optical pumped magnetometry. So for magnetometry, we will also meet the same situation. Like we cannot, no matter increase the atom number or photon number, there will be a limit. So sooner or later, if we meet the back action limit or the damage threshold, so we will need to have quantum technology. But also, as I said, to use quantum technology in very low particle, very bad sensitivity is not necessary. We can just increase the particle number. So to have a real advantagement, we will need a very good cooperation between the classical technology and quantum technology. So the first thing we do is to improve the sensitivity in classical way. So we are using paraffin coated cell to suppress the spin wall collision. So these cells are made by Misha, and they are both nice cell, and usually the T2 can reach to over 10 milliseconds. And then we also want to suppress the spin exchange. We know the most sensitive atomic magnetometry for now is the spin exchange relaxation-free surf magnetometry. So, but it usually operated under very low magnetic field or very high temperature. So it will limit its application. For sometimes we need to measure earth field. It have a high magnetic field, and the surf doesn't work. But there is another technique called light narrowing to offer a way to reach surf region. But this is usually be observed at the cell with the buffer gas, because with buffer gas, the buffer gas will add pressure broadening, and for a single light, it will interact with both hyperfine levels. But in our cell, we have no any buffer gas, and then we will need a repump beam. So with both pump and repump beam, atoms are polarized to F equals to MF equals to ZMS level. So then the spin exchange between the atom at same level will not induce the mechanism of dephasing. So this can suppress the spin exchange. So also with the repump beam, the polarization you can see here, the polarization is also is larger, and can also have prolonged the coherent time. So we have tried this experiment. So it's quite easy to see the signal be amplified. But for the line width, there were some pioneer work about seeing the light narrowing in the paraffin coated cell. So they will meet a problem about radiation trap. So what we do is we operate the magnetometry in FID, free induction decay scheme, and we pump the atom and turn it off. Then we just measure its freely decay. Then there were no problem of radiation trap. So we can clearly see there's a drop of the relaxation rate with the increase of the pump power. So also, magnetic gradient is a very common decoherence mechanism. So even if we want to study the magnetometry and in the magnetic field, if we want to apply a Earth field range magnetic field, it is very easy to generate a magnetic gradient. So then the atom located in different position will sense different Raman frequency. So after processing for a while, they will have different phase. That's also an dephasing mechanism. So what we do is we optimize the position of this coil. It's like using machine learning. It's a hybrid algorithm of differential evolution learner and artificial neural network. So our results shows the inhomogeneity reached 0.069%. So this inhomogeneity is good enough for our experiment. So then the last thing we want to cancel is the magnetic noise, especially for when the sensitivity is quite low. It's quite sensitive. So we will definitely see lots of magnetic noise. So there's a conventional way to reduce this noise. It's called gradiometer. We also apply a phase lock loop. It will also increase the bandwidth of the sensor and reach a very high common mode rejection ratio. So okay, with all of this, we manipulate the magnetic field and using a paraffin coated cell and suppress the spin exchange by the pumping and suppress the magnetic noise with a gradiometer. After all of this, we apply a quantum entangled light to squeeze the photoemission noise. So let's review the protocol of the gradiometer. So for a single sensor, it can measure both magnetic field, magnetic signal, and the magnetic noise, but they are just combined together and we cannot split it. Then it will have a very low signal to noise ratio. Then with the gradiometer, we use two cells. One can be a bit closer to the signal source, and another one is just as a reference to monitor the magnetic noise environment of the magnetic noise of the environment. So with the differential measurement, it can like just cancel off this common mode magnetic noise to increase the SNR. But we can look at this scheme in a quantum mechanical way. It's like this scheme actually increase the quantum noise because the sensitivity limitation is 1 over square root particle number. This is because the signal is proportional to the number and the noise is proportional to the square root of number. So then we can get 1 over square root. And but in this scheme, the signal only contributed from the upper channel. So the lower channel only monitor the noise. So it does not contribute to signal, but it also contributes to noise. Although it's a differential measurement, but these two channels have independent Gaussian white noise. So it still like increase the quantum fluctuation. And if we want to have more like, for example, MEG, there are like hundreds of sensors cooperating together, and this will increase a lot of noise. So what we do is we use entangled light to spread the quantum noise. We use a parametric amplifier to generate the correlation between the quantum correlation between these two channels. So after it's sensing the magnetic field, not only the magnetic noise is correlated, but also the quantum noise. So with the differential measurement, they can both be suppressed. So what we do is we use rubidium-85 to generate entangled light by four-wave mixing process and sensing the field using rubidium-87. There are two reasons to do that. So these lights are used as the probe beam. So the probe beam for magnetometry usually need to be a bit far off resonant to only consider first order atom light interaction. So the light generated from rubidium-85 have 2 GHz and 8 GHz detuning from the rubidium-87 transition. So that's how it's like a bit far off resonance. And also the quantum light is afraid of external loss. This will decrease the quantum enhancement. So with 2 GHz and 8 GHz detuning, the transmission of these two lights can be both like over 90%. So it's also good enough for our measurement. So the light directly, so if we directly measure the light generated from rubidium-85, we can see 7 dB squeezing of this light. After these two lights passing through the cell, we can see 5.5 dB. So this is caused by external loss. And also we can couple the magnetic signal here at 150 kilohertz. So for gradiometer, ideally we want to have exactly same response to the common mode magnetic field. But for our the probe, our probe is from at atoms, so they have different frequency, so they cannot be exactly same. So what we do is we tune we manipulate the amplitude and the width of these two resonances, and to make sure they have same response at the center. So the blue and red line are the two resonances from two sensors, and the black line is the result from gradiometer. So at the center, if they have two semi-response, the slope could be 0 for the black line. So they will have no response to common mode field. But for the gradient field, these two lines move to the opposite direction. So they will have a huge response here. So that's how we measure the gradient field and remove the response to the common mode field. So with the common mode rejection ratio of 5,000 and the squeezing of 5.5 dB, we can reach the sensitivity of 18 femtotesla per square hertz. So this is a result last year. So this year we generate a new type of polarization entangled beam. So last year we just used one parametric amplifier to generate entangled light. Now we use two and these two beams have a perpendicular polarization, and they are combined with a polarization beam splitter. And we found this light source can squeeze 3 Stokes operator at the same time. So this suggests us to generate like vector field measurement. We can squeeze both amplitude and direction of the magnetic field simultaneously. So since 2010, Morgan induced the idea about magnetometry with squeezed light. People keep pushing the sensitivity lower and also the frequency lower because there are lots of applications here. So last year we reached the 18 femtotesla, and with the new type of entangled light, we reached 6 femtotesla per square hertz this year. And also we induced the idea to the electronic field measurement. We changed the observation from polarization to the absorption. So that's how they measure the electronic field. And using a rubidium Rydberg atoms and couple the microwave with these atoms, and also have found some quantum enhancement. This is in theory work, and we will have a poster about this. So the rest time I'd like to introduce about our work about spin squeezing. So our talk starts from nonlinear Zeeman effect. So it's a bit surprise because usually people regard this effect as a drawback. It's only like induce splitting and the broadening of the resonance, and this will destroy the sensitivity. And sometimes with misalignment between the field and the sensors, they will have asymmetry resonance and lead to heading error. There are a lot of works. We also did some works about suppression or cancellation of nonlinear Zeeman effect. But if we write the effective Hamiltonian of NRZ effect and compare it with the one-axis twisting Hamiltonian, we found these two Hamiltonian have same form. So people usually describe the evolution of the atom using coupled basis. It's F is the total angular momentum coupled with electronic spin and nuclear spin. And with the NRZ effect, the spin state can undergo collapse and revival, and keep conversion between, we call it orientation and alignment, these two states. So we can also look at this state evolution in uncoupled basis. And we found for a coherent spin state, this is actually a direct product of the spin state of nuclear spin and electronic spin. And for the alignment, this is actually a entangled spin state. And for this state, it's reached to the maximum entanglement. So we can definitely find some way to make use of this entanglement and squeeze the noise. So, but nobody have ever seen the squeezing of the noise with the existence of NRZ effect. So we wonder why, and we calculate the variance of the traditional observation. So it's like a spin projection along a x direction, and we find it's always anti-squeezed. So maybe that's why people never see how it can be squeezed. And also we need to suffer from the decrease of the signal. So this is commonly used, regarded as a drawback. But after the rotation, the spin state along the polarization axis with a certain angle, we can find for a certain angle it can be squeezed, and it's quite large squeeze degree. And considering both the noise squeezing and the change of the signal, so we plot the change of the SNR, and it's keep oscillating with the time. At the maximum point, it can reach about 3 dB metrological gain. And so for the experiment for just spin squeezing, we can like use a nonlinear Hamiltonian to squeeze the noise and then turn it off, and then use the state to measure the, for example, phase. But at here, the mechanism to squeeze the spin and the thing we want to measure are same, are both Earth's magnetic field. So we cannot just turn it off. Then the state will keep oscillating from like maximum SNR to, for example, these are very low SNR. So on average, it's still not a very like good result. So we need to lock the spin state at the optimal point, keep the state here. So we also had some experiments about lock spin. So in 2018, we tried to spin locking and lock the state to a coherent spin state with a continuous RF field. And we also did some work about like optical manipulation and switch the continuous RF field to the pulses field using a dynamic decoupling scheme. This will also suppress the power burdening of the RF field. So if we want to lock the spin squeeze state, we just let's say about the mechanism of how we lock the coherent spin state. So we let the spin evolve for a certain very short time before it evolve far away from the initial state is the coherent spin state. We flip the spin from here psi t1 to here psi up 2 pi minus t1. Then let it evolve for the same time. It will just go back to the initial state. So for spin squeeze state, we just let it evolve for a longer time, then reach to the maximum squeezing, and then flip the spin doing this. And we also, so how to like flip this spin? We calculate the density matrix, this term, rho 02. This term is enough for lock the coherent spin state. We calculate the amplitude of this term and the phase of this term, and find for psi t1 and psi 2 pi minus t1, they have same amplitude and opposite phase. So we just need to shift the phase of this term. Like this is the scheme for locking the coherent spin state. So we only need to consider these two terms, and with 90-degree pulses in y direction, these two terms can be flipped and evolve for the same time. It will just go back. So that's how we lock the coherent spin state. But for the spin squeeze state, there are a lot of terms need to be considered. There are more terms, and they both need to have, after the spin manipulation, they need to both have same amplitude and different opposite phase. So we again ask help from machine learning. So we set an target function that says fidelity for the final state to the maximum squeeze state, and the computer will tell me what's the sequence for these pulses. And the result shows. So we have two target function. One is we want to optimize the final state after all of these manipulation. So this will give the best fidelity after one total cycle. But for sometimes we also want to continuous monitoring the spin evolution during the DD operation. So we also have another target function. It's average fidelity. So this will have a better long-time stability. So let's just conclude and outlook. So we are trying to have a better sensitivity and try to measure the vector field, and we will try to measure the biomag measurement. And we also found that the non-resistive effect is related with non-Hermian physics, and we also did some research on this. Okay, thanks for your attention.